this. And so when we look at the structure of amide, then we'll just go down the rules here. Nitrogen has how many valence electrons? And then we have two hydrogens, so 2 times 1. And then we have a -1 charge. -1 charge means we add an electron or remove an electron? Add electron. So 8 electrons. And so we've got to keep track of that number, and then we build the skeleton, or just some base structure. And so we'll put nitrogen in the center. Hydrogens can't go in the center, and then we'll just stick hydrogen on there. And so far, how many electrons have we used up? This would be 2, 4. 4 electrons we've used. And so how many electrons do we have left over? We have 4 electrons left over. Now, typically we complete the octets to the terminals first, but the terminals don't need any completion because the terminals are happy with a duet, the terminals being hydrogen here. And any remaining electrons we'll put on the central atom. So on nitrogen we'll put the remaining 4. And so that should be it. Okay, so this is the amide ion. Now, what else do we do with this? Now, if we're given a structure like this, what else do we do? With the net charge is the sum of the oxidation states, or the net charge is the sum of the, what was the other kind of thing we looked at? Oxidation state and formal charge. So when we do Lewis structures, we automatically do the formal charge. We don't automatically do oxidation states. Because oxidation states tell us about the redox properties. You know, formal charge is going to tell us something about the Lewis structure and the acid-base properties. And so let's take a look at the formal charges here. This hydrogen, how many electrons does this hydrogen have? Now, when we think about how many electrons this hydrogen has, we have to think in terms of, is it winner takes all, or is it a 50-50 split? Excuse me. What is it? Winner take all or 50-50 split? 50-50. And so if we split these 2 electrons, one goes to hydrogen, the other goes to nitrogen, and the hydrogen ends up with 1 electron. Hydrogen is supposed to have 1 electron, which means it breaks even. You know, each hydrogen donates 1, and it ends up with 1, so the formal charge is 0. Normally we don't write the 0 formal charges. We only write the non-zero formal charges, so I'll leave it blank. How about this nitrogen? It has 6. How many did it contribute to the structure? 5. Therefore, it came out ahead, 1 electron ahead. If it comes out 1 electron ahead, then we give it a negative or positive? Negative. And so the formal charge on this nitrogen is negative, and this hydrogen is just like this hydrogen, so it's 0. And so we sum up the formal charges, we get the net charge. So 0 minus 1 plus 0 gives us minus 1. That would be amide. Okay, let's go on to the next example. Here. The next example is the next example is HCl3 minus. What's HCl3 minus called? Bicarbonate. Give me another name for bicarbonate. Hydrogen carbonate. That's what they called it here, hydrogen carbonate. So we have the hydrogen carbonate ion. We're going to do the same thing. Hydrogen, how many valence? Carbon? 3 oxygens. Each oxygen is going to be 6. And and then the -1 charge, which means we add electron or subtract, add electron. So this is 3 times 6 is 18, 19, 20, 24 electrons. 24 electrons. Then we're going to put the least electronegative atom in the center. Which one's the least electronegative? It's not always, you know, but in general, the least electronegative goes in the center, which would be, in this case, it would be hydrogen. Hydrogen should go in the center, except there's a problem with putting hydrogen in the center. What is the problem with putting hydrogen in the center? It's not supposed to be in the center. Why?
Because it can only share one.
Yeah, it can only form one bond. And so hydrogen doesn't go in the center. So even though hydrogen is the least electronegative, we aren't going to put it in the center. We'll put carbon there. And then we have 1 hydrogen and 3 oxygens. Like that. So that looks okay. How many electrons have we used? 2, 4, 6, 8. So what we do next is any other electrons, we try to complete the octets to, these are the terminal, this is the central. So we'll try to complete the octets to the terminal. Well, hydrogen doesn't need an octet. Hydrogen needs just a duet. And so this is fine. But oxygen needs an octet. And so let's go ahead and put electrons there, here, and here. So that gives us 2, 4, 6, 8, an octet around oxygen. Carbon has an octet, 2, 4, 6, 8. So does that look pretty good? Yeah, everything has an octet. But I need to make sure, you know, I didn't use too many electrons, or not enough. I should have 24 electrons in the structure. And so let's count up the electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. This structure has 26 electrons, but I only have 24 electrons. So can it be this structure? No, it can't. Well, it can. I just have to remove. How many electrons do I have to remove? 2. So I have a choice here. Maybe to be fair, I'll just take off 1 electron off this oxygen and 1 electron off this oxygen to try to be as fair as possible. And so if I take 1 off this oxygen, 1 off this oxygen, is that okay? No, this is not okay. Why? It's not stable. Why is it not stable? Yeah, this is not quite an octet, but you know, I'm kind of stuck because I only have 24 electrons. But there's another issue with this. Do you see the other issue? Other issue is you've seen these kind of things before where there's just a single electron. When you see a single electron like that, do you know what kind of species that is? It's a what? It's a radical. Yeah, it's a radical. Well, it's not just any radical, it's a free radical. Are free radicals stable? No, they're very reactive. Is bicarbonate stable? Yeah, somewhat. I mean, you can buy it at the supermarket. Do you know what they put bicarbonate in? Like baking powder has bicarbonate, right? Baking soda is all bicarbonate. Baking powder has some other stuff in addition to the bicarbonate. And so, yeah, it's not likely that this has, yeah. So even though this is the right number of electrons, 24 electrons is right, I don't think so for this one. So let's eliminate that. Well then, how about we'll just take 2 electrons off 1 oxygen. That way we can leave these paired up. And then this one will have an octet. And so 2 of the oxygens will have an octet, 1 of them won't. How's that? Well, it's good that this has 24 electrons, but it's bad because this is lacking an octet. It's not an octet. So is there another way to distribute the electrons here? Can you think of another way that we can distribute the electrons such that everybody's happy? So do you have it?
No, never mind. I changed my mind.
Okay. Well, take a minute and come up with a better plan to distribute the electrons so that everybody's happy.
Form a bond. Oxygen and hydrogen.
Form a bond from oxygen and hydrogen like this.
And not the carbon.
Oh, okay. You mean a completely different structure. Yeah. After you take a few minutes and think about this, is there any way to make this work? No. In fact, this just isn't going to work. And so that's a great suggestion. What we'll do is we'll bond the hydrogen to the oxygen. How about like this? And then the carbon?
Yeah.
Okay, let's try that. And so we're going to go hydrogen, oxygen, carbon. Something like that, but it looks like this carbon might end up being short, but it's okay. So how many electrons have we used? 2, 4, 6, 8. Then we're going to complete the octets. This is called a bridging oxygen. This is called a terminal oxygen. We complete the octets to the terminal oxygens first. Like that. And then we'll complete the octet to the bridging oxygen. Like this. But, you know, this carbon is short of an octet, so we'll just throw in another lone pair there. And that should do it. Let's check it out now. So how many electrons do we have? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I have 26 electrons, but I don't have 26 electrons. I only have 24 electrons. I have 26 electrons in the structure. I have too many electrons. So I got to get rid of 2. If I get rid of 2, who should I take them from?
Carbon.
The carbon. So I'm going to just take them from the carbon. But this structure is not good too. We just have the same issue. No octet. So I'm back to no octet here. Right, the octet rule has been violated here because I should have an octet of electrons around carbon that will stabilize it.
You do a double bond?
Right. In this case, in this case over here, there's no way to resolve it. In this case, there is a way to resolve this. The way to resolve this is this. We're going to ask one of these oxygens here to sacrifice an electron pair. In other words, we're going to convert a lone pair into a bonding pair. And so if we convert a lone pair into a bonding pair, what happens, let's just take this one for example. If we convert that into a bonding pair, oxygen still has an octet, but now carbon has an octet as well. And so we have 3 choices here, because we have 3 oxygens. So which oxygen is willing to sacrifice a lone pair to create a bonding pair so that the carbon can have an octet? So is it oxygen 1, or oxygen 2, or oxygen 3? Which one will sacrifice? 1? Okay. So let's see, if oxygen 1 decides that it's going to sacrifice the lone pair, so we'll take this lone pair, bring it into the bond, we're going to end up with this structure here. We will end up with a double bond here to the carbon. Now carbon will have a total of 4 bonds. That's good because that'll give it an octet. 1 double, 2 singles. Okay, so let's now check. Hydrogen has a duet. This oxygen, does it have an octet? Yeah, 2, 4, 6, 8. Does carbon have an octet? Yes, 2, 4, 6, 8. Remember, we double count for octets. Does this oxygen have an octet? Yeah, and this?
Yep.
Yeah, so this is good. Everything has an octet. Yeah?
When we originally had the hydrogen on the carbon,
Mm-hmm.
when we do it like that, but had one of the oxygen double bonded, would that also make sense?
Okay, like this oxygen here?
Right, yeah.
If we double bond this oxygen here, like this, it's still lacking an octet. Because the double bonding electrons have to come from one. Now, if I took it off this oxygen, fine, but if I say, okay, I don't want to take it off that oxygen, I'll take it off this oxygen. If I take it off this oxygen and put it over here, then this oxygen is going to not. There's no way, I mean, you could play around with this for a half an hour or an hour, and there's no way you're going to rearrange the electrons so that everybody's happy. You can't do it with this structure. And so, you know, well, maybe this is it. Maybe this is the best. But what we should do is we should just play around and see if we can get a better structure in which everybody's happy. And so going over here, is everybody happy here? Yeah, everybody's happy here because everybody has an octet except hydrogen, which has a duet. And so everybody's happy here, right?
Did you put the double bonds on any of the other oxygen?
Yeah, well, what if we pick this oxygen number 2? If we picked oxygen number 2, let's see what happens. We would generate a different structure a little bit, in the sense that this would be the double bond here instead. And so when we look at this structure, does everybody have an octet? Everybody has an octet. So that looks good. And then what if we picked oxygen 3? If we picked oxygen 3, then we generate this structure here. Does everybody have an octet?
Yeah.
Yeah. And so it looks like these 3 structures are good. But they aren't the same. They aren't the same because, you know, the net charge comes from what? All these are ions, so we put the square brackets in the net charge on the outside. The net charge is either going to come from the sum of the oxidation states or it's going to come from the sum of the formal charges. So the formal charges have to add up. Well, what's more important for Lewis structures? For Lewis structures, we care about formal charge. We don't necessarily care about oxidation state and looking at structures. And so looking at this structure, what are the formal charges? So the formal charge on H has how many electrons in this structure? 1. Well, it gave 1, so it broke even. Formal charge is 0. This oxygen, how many electrons does that oxygen have in this structure? Well, when we count it, we split this down the middle. So 1 dot goes to the oxygen. So that's 1, 2, 3, and then split these down the middle. A double bond consists of 4 dots. 2 of the dots will go to this oxygen, the other 2 will go to the carbon. And so it'll be 1, 2, 3, 4, 5. So there are 5 electrons. That oxygen has 5 electrons. How many did the oxygens contribute? 6. So it ended up with 5 electrons in the structure, but it contributed 6, which means it will be positive. Okay, so that's positive. How about this carbon? No, the carbon is 0. Why is it 0? Because it ends up with, we'll split these down the middle. 1, 2, split this down the middle. 3, split this down the middle. 4. It ends up with 4 dots. 4 electrons. How many did it contribute? 4. So it broke even. If it breaks even, it's 0. And so this carbon's 0. How about this oxygen over here on the right? We count them this way: 2, 4, 6, and then 7. So it contributed 6. It ends up with 7, which gives it a charge of -1. Yeah, this is minus. And this oxygen? Okay, so those are the formal charges. Let's go to this next structure here and do the same thing. The hydrogen formal charge is it's 0. Its oxidation state is 1, but its formal charge is 0. This oxygen is 0. Carbon 0. This oxygen 0. This oxygen -1. So when we look at this, this is how we distribute the electrons. So if we look at this, we're definitely going to have a formal charge there, a net negative, because the charge on the whole thing is -1. Therefore, the formal charges have to add up to -1. So that's 0, 0, 0, 0, -1. It's going to be -1. Over here, the formal charges must add up to the net charge. So this is 0, +1, 0, -1, -1. So -2 + 1 is -1. And so the sum of the formal charges is equal to the net charge. But the formal charge distribution, which one is more fair? Which one is a more fair distribution of electrons? The first one or the second one? The first one is more fair. Because if you think about this, think about this oxygen. This oxygen came out the loser, this oxygen came out the winner. If there's a tug of war between 2 oxygens, this oxygen is the loser oxygen, this oxygen is the winner oxygen. So imagine a tug of war between 2 oxygens. The left oxygen is going to be the winner, the right oxygen is going to be the loser. Is that right? Is that always the case? The left oxygen is the loser oxygen, the right oxygen is the winner oxygen? Or does that seem a little weird because oxygen should have the same pulling power? And so this is unstable. This would be unstable because one oxygen lost to the other oxygen, but it doesn't really make much sense because both oxygens should be about the same. And so I would say this structure is better than this structure. In fact, this structure is not looking so good. That structure is not looking so good. You know, it's not because having a positive charge on oxygen is bad. We see positive charges on oxygen. Like, for example, this. What is the formal charge on oxygen here in H3O? +1. The hydrogens? The hydrogens are all 0. And so this is going to be H3O plus. H3O plus, you've seen that before. H3O plus is called H3O plus. It's on the acid chart. It's called hydronium. This is hydronium. If you recall, H plus is terribly unstable, but we use H plus all the time. When you see H plus, we're really talking about hydronium because H plus will react immediately with a water molecule to form hydronium. And so it's not having a positive charge on having a positive charge on oxygen sometimes is unavoidable. We'll have a positive charge on oxygen. It's just that this positive charge means this oxygen lost. That's okay, oxygen can lose. But who did it lose to? Another oxygen. Does that make sense? No, and so this is why this one's unstable. But this one's good. How about this one? This one's good too. When we look at it, all the formal charges are 0 except for one. Which one?
The one above.
The one on the bottom?
The one on top right.
The one on the top right. This one is
Negative.
negative. And so actually these two, do you expect any difference in the energy?
No.
No, in fact these two are essentially the same structure, but they aren't the same. They're the same because they're going to have exactly the same energy. They aren't the same because we had a choice of where to sacrifice, which oxygen was going to sacrifice. And either one of these were okay. And what we call this is we draw a little double-headed arrow, and we call these two structures resonant forms or resonant structures. Resonant structures. And so both of these are good here. In fact, some people, when they think about resonance, they think about resonant frequency, you know, something vibrating at some frequency. Yeah, like, did I show that video of the Tacoma Bridge in Washington? No? Oh, that was the classic one. It turns out that, you know, it used to be that people didn't care about the resonant frequencies of buildings and structures. And nowadays, all buildings and structures are tested for resonant frequency. They want to make sure that the resonant frequency isn't something that can be ever hit. But it turned out that the Tacoma Narrows Bridge was never tested.
I've had enough. I'm sick of seeing and touching both sides of things. Sick of being.
I don't know what the audio
Nobody can talk to anybody without me.
So, you know, a lot of the energies are forbidden. The energies are forbidden, they aren't absorbed, but it just so happened the winds were blowing, and that was an allowed energy. And if it's allowed energy, then it's going to absorb that energy. The bridge will start to absorb that energy. And so this is the bridge resonating at the allowed energy here.
Never tried
That would be pretty fun. That would be like the like carnival.
I like when two people jump on the bed.
We all know.
And just lock somebody on their bed.
It's hard as hell.
It's exactly.
The bridge not losing the wind, like what? No, like it's not built to do that. I really hope not.
It's a brand new bridge.
It should not be bending that way. No, but the bridge should not be like twisting like that. Well, yeah.
This has got to be like Photoshop or something, or whatever they call it. Yeah. After Effects.
Oh yeah, running He barely made it.
Well, yeah, it shouldn't be bending like that, and that's what's going to happen if it bends too much. Fatigue structure. So now, nowadays they'll test the make sure the resonant frequencies, the frequencies of the building, the natural frequencies, because these types of things are quantized as well. They'll make sure that those aren't hit.
Wait, so that happened just because the wind's blowing?
Mm-hmm. That's crazy. That's physics. It opened in July 1st, 1940, and it collapsed a few months later. Yeah, longest twin suspension bridge in the world.
How'd they fix it?
Well, they just made sure that,
They had to tear it down. They can't like patch it.
yeah.
They obviously rebuilt it.
They rebuilt it, but they didn't rebuild it the same. They just made sure the resonant frequency of the bridge didn't match. Tacoma Narrow Bridge. So winds blow across, nothing happens because those are forbidden. And then winds hit a certain speed or a certain whatever, and then it starts. It hits that right energy, then it starts being absorbed. Okay. Anyway, we're. And he's not here. So what some people think that this is resonating as well. It kind of makes sense. We're calling these resonant structures. And so some people are thinking that the negative is resonating back and forth. Like the negative sign goes from this oxygen to this oxygen, back and forth, like this. And then also the double bond. Do you know double bonds are shorter than single bonds? And so some people are thinking that the bonds are resonating too, like back and forth, like this, resonating. Because this is going from double to single, back to double. And so it's just resonating like this. But it turns out that it's not resonating. What we have here is the true structure is going to be the hybrid structure. We'll talk about that. So we just derived the resonance structures, 2 or more equivalent Lewis structures for molecular ion that are created by changing only the positions of the electrons, in which the actual species is an average. So only, let me stop there for the first part. We only change the position of the electrons. We never change the position of the atoms. So if somebody were to ask, what are the resonance structures for bicarbonate, then there are only 2. But sometimes when I ask this question on a test, I get a lot more than 2. And so the 2 structures would be this. We had a choice. We could make the double bond to this oxygen, or we could make the double bond to the other oxygen. So if we made it to the right oxygen, we end up with this. If we made it to the bottom oxygen, we end up with this structure here. Again, double bonds are shorter than single bonds, so this is why I'm drawing them like this. Okay, there's a negative formal charge here, a negative formal charge here. The total charge is -1. The total charge here is -1. Okay, we show that these are resonance structures by drawing the double-headed arrow like this. So the double-headed arrow says these 2 structures are the same, but they aren't the same because there are 2 ways to make this structure. They aren't the same because when we do resonance, we only move electrons, never move atoms. And so if we leave the atoms fixed in position, then the way we move the electrons is like this. There are 2 ways to distribute. So for example, if I'm in this resonance form, I could switch to the other resonance form by doing this. I could switch to the other resonance form by dropping a lone pair into the bond here. Well, if I drop a lone pair into the bond, that makes more than an octet around this carbon. So what I'm going to do is kick 2 out, like this. And so take 2 in here, kick 2 out there, I switch to this structure. And then I can switch back to the other structure here. I just take two, put those into the bond here, create a double bond, and then kick two out here. And so this is what we mean by only move the electrons. So we redistribute the electrons here, we can interconvert between the two resonance forms. We never move the atoms, so sometimes when somebody tries to draw resonance structures, what they end up doing is they end up moving the hydrogen. And so when I look at their structures, in one structure they have the hydrogen on the left. And then they try to come up with another resonance form. And the next resonance form, what they do is they move the hydrogen atom to the bottom. Like this. And so they keep moving the hydrogens, and then they start moving the electrons, and pretty soon they have like 5, 6, 7 different structures there. And they're taking a long time for the test. And so this is wrong. We never move the atoms. We just reposition the electrons. Well, you know, this repositioning the electrons, this just happens, you know. In other words, we have two terms that we use when we're describing electrons like this. One term is, we have a term called delocalization of electrons. And so what delocalization means is electrons can move a little bit versus localization. Localization of electrons means they can't move. So for example, can I reposition this lone pair? I want to take this lone pair and make a double bond to the hydrogen. Is that acceptable? No. Or let's make this single bond into a no bond and then just give it to the oxygen. Is that acceptable? No. So these electrons here, I cannot move. There's no way to move these electrons, so these are called localized electrons. However, these are called delocalized electrons because there is a way to move them. Now, when I have delocalized electrons, I have to envision a cloud. If you have a fog cloud, is a fog cloud localized, or does a fog cloud delocalize and spread across the area? The fog cloud delocalizes and spreads across as much as it possibly can, right? And so one way of thinking about the resonance forms is like this. One way of thinking about these resonance forms is, in this case, I have a double bond top right, single bond bottom. And so I can think of like a bathtub. The electrons are going to be delocalized over this L here, like this. And so the oxygen at the top right has twice as many electrons, and so we'll call that like 2 feet of water. And so this has 2 feet of water, and then that would be the double bond here, and the single bond would be, let's say, 1 foot of water. And so the single bond will just make 1 foot. This is fine. And then the other resonance form, we're going to move. Okay, we'll just move a foot of water to the other side. And so now we're going to have 2 feet of water here, and then 1 foot of water here. So this is going to be 2 feet. This is going to be 1 foot. This only works if we can localize it. If we can localize it, how can we localize? We have to put a wall here. If we build a wall in this bathtub, then we can have one side of the bathtub 2 feet deep, the other side 1 foot deep. But is there a wall there? Well, there's a wall here. You know, I can't really move the electrons here. These are localized. But is there a wall here preventing me from moving the electrons or redistributing the electrons? There's no wall here. In fact, if I move these electrons here, that'll kick these electrons out. And so really, neither of these structures is the correct structure. The actual structure is, okay, we'll just read the last part of this sentence, in which the actual structure, actual species, is an average of the resonance structures. So what's going to happen here? if the electrons can move like water, or if the electrons can move like fog, then I'm not going to get 2 feet and 1 foot. I'm going to get 1.5 feet. And so the actual structure, and so this will be called what we call this is the resonance hybrid. The resonance hybrid is an average. And the resonance hybrid is going to be the actual structure. And so the actual structure is going to look like this. Rather than having 1 foot and 2 feet and 2 feet and 1 foot, I'm going to have 1.5 feet of water. And so this will be 1.5 feet. This will be 1.5 feet. And so the electron cloud is just going to do this. The electron cloud isn't going to bunch up here, and then all of a sudden bunch up here, and then bunch up here and back and forth. The electron cloud is just going to spread out. That spreading out process is called delocalization. So the electron cloud is just going to delocalize over wherever it can delocalize, because the electron cloud consists of negative charge density, and to help stabilize it, we want to spread it out, spread it thin. And so this is called the resonance hybrid. And so the resonance hybrid for this is going to look a little funny. Just draw it over here. It's going to be the average of those two structures. Now, how do I average those two structures? Well, the H, so this will be the resonance hybrid. Nothing happens to the H, O, C. That's all localized. But what's going to happen is this, over here. There's going to be 2 single bonds that are permanently affixed to the oxygen. So these 2 single bonds are always there. Don't want to over-exaggerate. There are going to be 2 lone pairs that are always on the oxygens. But there's going to be 1 lone pair that floats between the 2 oxygens, so it's going to spread out between the 2. So I'll just draw this as dashed here. So what's going to happen is it's not going to be -1 in one instance and 0 in the next, or 0 and then -1. We're just going to average it. And so the average of -1 and 0 would be -1/2. And so the charge here is going to be -1/2. The charge here is going to be -1/2. And so we're going to take that cloud and spread it over 2 oxygens like that. Now the double bond, we're going to spread out over 2 bonds. And so I'm going to dash it like this. And so it's not going to be a single and a double, or double and a single. Both bonds are going to be exactly the same. And both bonds are going to be a 1.5 bond, or 1 1/2 bond. So this will be a 1.5 bond. And so the electron cloud just smears out or delocalizes over this portion of the ion. Still, the net charge is the same. You know, -1/2 plus -1/2 gives us -1. And so this would be the resonance hybrid. This would be the true structure, because when we analyze the structure of bicarbonate, you find that both of these oxygens have the same charge, and both of these bonds are exactly the same. And so it isn't resonating, the resonance hybrid is it. But how did we figure out the resonance hybrid? We first do the resonance structures and then average those. All right, isomers is the next topic on the slide, but isomers doesn't belong here. Isomers is separate, so this is not related to isomers at all. These are resonance structures. Isomers are something totally different. What isomers are they're 2 compounds having the same molecular formulas but have different structural formulas and different physical and chemical properties.
So if you were to ask us for the Lewis dot structure of bicarbonate, you would want the resonance hybrid structure?
No, I would want these two here. Then, as a bonus, I might ask you to draw or sketch the hybrid. But when we do it, we just draw all these and then try to visualize what would the average of all these look like. Some species will have more than 2 resonance structures. Some will have like 3. Some will have even more, 4. And it just depends on how many choices you have for forming the double bond. Uh-huh.
I don't really get how something can have like half a bond, like 1.5. Like, is that
How it has it is,
like, is that or is that just a science thing that we do?
how can it have? You're saying like how can something have half an electron? It either has one electron or half electron. How it has half a bond is a bond is defined by how many electrons you cram between the atom. So if you fit 2 electrons between the atoms here, we call it a single bond. If you fit 4 electrons between the atoms here, we would call it a double bond. 6 electrons would be a triple bond. And so essentially what we're doing is we're cramming 3 electrons in this, 3 electrons worth of electron cloud.
So
And
it's
that's
just the average.
Yeah,
Okay.
that would be the average. And so this would be 1.5 worth of electron cloud in there,
Okay.
if that makes
Yeah.
more sense. But we only do that for the hybrid, this one. Now, conceptually, this is difficult, but this is a lot easier because when we're looking at the individual resonance structures themselves, we just pick one and then analyze that. And we ignore this one. So if we just pick this one, then we got a double bond and we got a single bond.
Okay.
We don't have to worry about 1.5 bonds. We don't have to worry about -1/2. We just worry about this. That's it. This is in quantum mechanics. It doesn't come out like this. This is what we call a light version of quantum mechanics. This is what we're doing. This is quantum mechanics light. In the full version of quantum mechanics, we don't even get resonance structures. We just get the hybrids spit out straight. But the problem with the full version of quantum mechanics is we need a computer to do the calculations. The advantage of doing this is we don't need any computer. We just need a pencil and paper. We can kind of figure it out. And so it's not perfect, but it's a lot easier. And it's not terribly far off. All right, those are resonance structures. We're going to look at isomers next. So isomers have the same formula, same molecular formula, different structure. So an example of isomers would be something like this, C2H6O. C2H6O. Let's draw out the Lewis structures for this. So 2 carbons has how many? 4 each. 6 hydrogens, 6 times 1. 1 oxygen, should be 6, and no charge. And so we got 8, 13, right? Maybe I screwed it up. 8, 14, 20. 20 electrons total. All right, which atom should we put in the center? Well, the least electronegative, which would be hydrogen, but for carbon. No, hydrogen. Hydrogen would be the least. But can we put hydrogen in the center? No, so we're going to go with carbon. And we'll put carbon in the center. So what should we attach to the carbon? All right, now this is getting a little bit tricky because there are multiple center atoms here. So maybe what we'll do is we'll attach another carbon. Because, have you heard of organic chemistry? Organic chemistry is the chemistry of carbon. And so why do organic chemists study the chemistry of carbon? Because carbon forms so many different bonding arrangements, so many different ways to link together. And one thing that carbon likes to do is it likes to form carbon-carbon links like this. In fact, let's take a look at some of these because some of these will help us figure out the structure of these, because these get a lot more complicated than the ones we looked at, like bicarbonate. We don't have that many choices, but we have a lot more choices here. And so when we look at carbon and the way carbon likes to bond, carbon likes to form 4 single bonds. If it forms 4 single bonds, it gets an octet. Or carbon would like to form 2 single bonds and 1 double bond. So if it forms a double bond and 2 single bonds, we get an octet. This is like bicarbonate. Or carbon likes to form 1 triple bond and 1 single bond. That would give it an octet. There's actually more. If we don't mind having a charge on carbon, then carbon can have a lone pair and 3 single bonds. But if carbon has a lone pair and 3 single bonds, what is its charge? Well, we split the single bonds in half. Actually, -1, because it comes out with an extra electron, so it's got 5 electrons. Or sometimes carbon will form 3 single bonds like this. It forms 3 single bonds and no octet. It's very unhappy, but what would the charge on it be? +1. And so there are some unusual bonding arrangements, but typically carbon likes to form 4 bonds unless it's got a charge on it. And so these types of things we keep in mind when we're building Lewis structure. The same thing with, well, we'll go to oxygen next. Well, how many bonds does oxygen like to form? What have you noticed? Well, oxygen's 2 electrons shy from an octet, so oxygen likes to form 2 single bonds, and it'll have 2 lone pairs. And so that's good. That's called what we call a bridging or terminal oxygen. Bridging. It's a central atom. Or oxygen would like to form 1 double bond with 2 lone pairs. This would be a terminal oxygen. That's okay too. Or oxygen would like to form 3 bonds, but if it forms 3 bonds, then what happens? If oxygen forms 3 bonds, then the charge does not stay 0. The charge is going to go to? No. +1. Or oxygen likes to form 1 single bond, but have 3 lone pairs. If oxygen has 1 single bond and 3 lone pairs, what's its charge going to be? -1. And so these are possible scenarios for oxygen, so we keep those in mind. You know, we think, okay, what are the possible links that we can have, and then we can build Lewis structures based on that. Nitrogen. What does nitrogen like to do? Nitrogen likes to have 3 single bonds in a lone pair. Right, we saw that in ammonia. Or sometimes nitrogen would like to have 4 single bonds. But if it has 4 single bonds, then what happens? It goes +1. Or nitrogen has 2 single bonds and 2 lone pairs. If nitrogen has 2 single bonds and 2 lone pairs, then what's the charge? -1. What's the charge on this? Let's put a double bond and a single bond in a lone pair. If I had the double bond, a single bond, and a lone pair, what's the charge? 0. And so nitrogen likes to form 3 bonds unless it's charged. If it's charged, then it can form a different number of bonds. How about fluorine? Fluorine likes to form just 1 bond. What would the formal charge on this fluorine be? 0. Well, what if fluorine, hey, can fluorine form 2 bonds and then be left with 2 lone pairs? Is this a possible bonding scenario for fluorine? And so we look, in order for that to happen, what does the charge on fluorine have to go to? This must be fluorine plus. Is fluorine plus a happy charge or an unhappy charge? Unhappy. In fact, fluorine is the most, what was that word? For ability to attract electrons? Electron cloud. It's the most electronegative element on the periodic table. This doesn't happen. Fluorine never forms a double bond. Fluorine does not form or does not double bond. Because in order to double bond, it has to give up a pair of electrons or share it. And it doesn't want to share it because charge is going to go up. Whereas over here it might, like oxygen. Oxygen is willing to share and get that positive charge. Fluorine would never share. Okay, so what we could do here is we could actually, we'll take a break and then we'll continue with the isomers. So.
Survey, Professor.
Okay.